All right. So what we're going to move on to next is looking at a general case for stress. And so, just as a quick reminder, all of the previous examples we have worked through, we were assuming that the stress was averaged out over equal over the a given area which was being stressed. So. We would have things like for an axial stress, we would just have P over A. So just as a quick reminder, previously for an average stress, we might be we might have an axial stress here where we have a force which was pulling this way, and we just assumed that our stress block had an equal level of stress all around to counteract that. So if this was our force T and this was our stress average. And as we discussed previously, this is not a bad approximation for some cases. So axial stress is one of those cases, particularly when you are towards the middle of the member and you're far away from any stress concentrations. However, there are lots of cases which it's not a good example. And one really common case where average stress doesn't work is really just in bending. So even for a very straightforward member, like a simply supported beam here, um, no good. So for a simply supported beam with a transverse load, this isn't going to work well, and so we need to determine. We need to basically derive what our stress state is going to be at different locations, both along the member as well as across that section. And so that's what we're going to do today. We're going to move from this to something that will help us deal with the average stress, not the average, the actual stress at a point for any given loading case. So we'll step back to our little diagram here. And so with this derivation, what we're going to do is derive it for a generic structure or body, if you would, with some arbitrary loading. So what I've drawn here, this little kind of peanut-shaped body with a number of different forces coming in at all different points. So we want to know, well, if we're going anywhere across or anywhere inside this body, well, what is the stress state at that point, and what is that stress state in relation to the stress which is normal to the surface as well as any shearing stress. So what we'll do is we'll take this little sort of cross section here and we'll draw that out, and then that's what we will work on our derivation with. So if I just draw that cross section out here, that's sort of the other half of that peanut section, and it's got some forces acting on it, and then we got one down here. And all right, so well, just like with average stress, a good place for us to start is if we want to look at the stress at a given point, is let's divide our cross section into a grid. And so working on that, we got our grid coming across here. And let's give some axes to this just to help orient ourselves. So we will call the z-axis vertical, and then we will just use the right-hand rule, which means that the x is coming down and the y-axis is going this direction. So if we want to find the stress at a point and then use that relationship to find it at any given point or over a whole distance of points, well, just like with average stress, let's just pick one of these boxes. And so we will highlight that one there, shade that in, and let's have a look at what the stress or what the forces are going to be on that. So we're going to call this little area, dA or delta A, similar to our average stress. So it's some small area, and if what we want to look at is stress at a point, well, we will allow dA to get smaller and smaller and smaller until it becomes as it approaches 0, that gets closer and closer to a point. But so as we talked about with all of our stress, external forces are going to create an internal action. This element has to act in it needs to be in equilibrium. And so if we think about, well, we've got all of these forces coming in at some random direction, well, there's probably going to be some resultant force, and we'll call that delta P. So that has some magnitude and some orientation. It's not necessarily helpful to us because, as engineers, we tend to think in either a coordinate system which is going to be relevant to either the member itself or the whole structure. And so what we would rather look at are, well, we know it's a vector, so we know it's made up of components. Well, let's look at the components in terms of our x, y, and z. And we'll just draw those out dashed like this. So we get delta P in the z direction, delta P in the y direction, delta P in the x direction. All right, so that's not too challenging. That's just this resultant force broken out. Well, now kind of what we have, if we've taken this slice in the xz plane, well, we can look at these in terms of a normal force and shear forces at a point. And so what we want to do, if we want to find the stress at a point, for stress at a point, well, then we just want to let this delta A get smaller and smaller and smaller. And then that force is just going to be that stress times that area. And as you get smaller, it's close to a point. So for stress at a point, we just want to let delta A approach 0. And we did that when we looked at average stress too. So this should all be very familiar. So like I said, each of these components, if we've taken this cross-section in the XZ plane, well, they really just fall out as normal and shear stresses. So for our normal stress, it's going to be the stress in the y direction. So it's a normal stress, so we give it the variable sigma. Well, that's just going to be as the limit of delta A approaches 0 of delta Py over delta A. So that makes sense. That's that force. So the stress is the force over the area, and the stress at a point, well, we just let that area get smaller and smaller and smaller as it approaches a point. The next, so that's our normal stress. Well, let's look at the two shear stresses we have. So we will do tau of y in the x direction is going to be the limit delta A approaches 0 of delta P x over delta A. So we'll talk about these subscripts here in a little bit, but I mean, that's at this stage, just think, well, we've got a normal force here, but we've got one shear force in this direction, so the stress is going to be that force over that small area. And then tau of yz is going to be the limit delta A approaches 0 of delta P z over delta A. So, I mean, it's a little bit of math there, but none of it's terribly complicated. All we're doing is just looking at essentially a free body diagram and looking at components, and then just using our definition of a stress of a force over an area, and to find it at a spot, well, we want that area to get smaller and smaller and smaller until it eventually becomes a point. So this is kind of useful for us, but it's we've pretty much just written a definition down here. If we want to know, well, what's our relationship of a stress state, and how does that relate to adjacent forces next to it? Well, we need to go from a section and really take out a tiny little cube from this box, and then look at what are all the stresses on each face. So let's do that. Let's draw this little cube in here. We'll just highlight that little cube in red. And we'll draw that out. And we're going to, again, this cube is going to be teeny tiny in order to get the stresses at a point. So I'll draw out our cube here. That's our first face. Bring it back. And because we've just pulled it straight out of here, we're going to keep the same coordinate system where z is going to be going up, y is going to be going to the right of the screen, and then x will be orthogonal to both of those. So here's our little cube. And let's just give it each side. We will say each side has length A, and A is approaching 0. It's really small, so we'll just say that as a definition, and we'll draw in the dash so that we've got the hidden sides, hidden faces there. So this is what we've started with. We've pulled it out of here. What we want is then to draw the stress state on here. Essentially, we want to, we've worked out what each of the stresses are on each of the faces. So on this first face, which was right here, we've already drawn that. So we have a stress sigma y. And then we also have a shear stress tau yz, and a shear stress going in the opposite direction. So going orthogonal, sorry. Tau y x. So we've just drawn this and basically this definition right here. For this block to be in equilibrium, well, we need an equal and opposite force on both sides. So on the opposing face, we also have sigma y, so normal stress at y. We also have a tau yz, and we have a tau yx. And then we can work our way around the face, and we actually, well, if we take a cut here, we would find that you've got, again, a normal force pointing up. sigma z. And then you've got a shear force, both acting orthogonal. So tau zy, tau zx. On the opposite side, again, sigma z. And orthogonal. So that's going to be tau zx, tau zy. So that's 4 of our sides, and then the last place where we could have some stress on this block is on the zy face. So normal to the x direction, sigma x, sigma x. Sorry, we're getting a little messy here on the drawing, but you should be starting to see the pattern. On every face, the potential stresses that we have are going to be basically a stress in each principal direction. So a normal stress and then a shear stress in each direction. That's what we could have. And then we'll just write that out. Tau x z and tau x y. So cool. And then you can think of this like when you first started learning free body diagrams. So what we want to do is put down all of the potential forces. In this case, we're looking at stresses instead of forces. But again, the force is just going to be that stress times the area. And then we want to set up our equilibrium equations and see, well, what's the relationship between them? Are they, do we have a force there? Do we not? Is it equal to 0? Is it not? And that's what we're going to work with. Before we then, so that's what we're going to do, is we're going to essentially do free body diagrams of each of these faces. But before we do that, I wanted to give you just a little bit of a sign convention so that while we talk about this, things make sense. So we'll work with this one first. So the easiest one is for our normal stress. So if we have, say, we've got sigma x, it's just our normal stress in the x direction. So that's pretty straightforward. Now we've got all of these taus for our shear stress, and I've got y-x's, x-y's. You know, what's the difference? And they do follow a pattern. So if I have, for example, tau xy, well, this is going to be our shear stress. And this will be on the x face, or you can think of this, that's the face normal to the stress. And then the second subscript will be in the y direction. So what we have, tau xy is going to be here. So it's on the x face. So it's the face that we've cut. So it's the face normal to the... so we've got our normal stress in the x direction. So it's this face here. So that's all right. And then in the y direction, it's pointing in the y direction. So tau xz will be on the x face pointing in the z direction. In terms of what is positive, what is negative for normal stress, so we'll just draw our over here. normal stress. Positive is tension. And negative is compression. For shear stress, we're really just going with the direction of the axes. Shear stress, so positive is just direction of axis. So you can think of tau yx is a positive shear stress because it's on the y face and it's pointing in the positive x direction, while the tau yx on this side is negative because it's pointing in the negative x direction. So that's what we're starting with. Now, what we want to do is, we've got our little shear block. We know what our sign convention is. Now we just want to find out, well, what's the relationship between all of these stresses? And once we have that relationship, well, then we can work through. Well, then we've derived what our stress is at a given point, and we can use that to find any arbitrary stress for really any structure. So, what we want to start with first is let's just look at the XZ plane. So we'll just look at this plane pointing in this direction, having a look, and we'll just draw what our stress state is there. So if we come back here, look at XZ plane, what does our little free body diagram look like? Well, we're going to call the center, we'll just call that C, just to give ourselves an orientation. The sides have dimension A, and then we have our axes Z, X, and that's just a direct. We're just bringing them straight from this this little block here. So what are the forces that we have on here, or in this case, actually, what are the stresses that we have? Well, we know that we've got a normal stress in the Z direction, and we know that there is a normal stress in the X direction. And then if we go back to our little block, well, we've got, so we're really looking at this face, this top face, and this bottom face. So we know that we have a shear stress ZX on the top, and that's going to be also down below. So on the top, it goes in the positive X direction. So that's our tau ZX. And on the bottom, we have tau ZX, but just going in the opposite direction. And then finally on the X faces, so on these two faces here, we have a tau XZ pointing up and a tau ZX pointing down. So we will draw those in. So tau, XZ and tau XZ. And maybe we'll just highlight those in red just to make them a little bit easier to pick out here on camera. So those are all of our potential stresses on this block. And I guess the last little definition that you need is that A times A equals dA. So that's just the area of this block with sides A. Remember, A is really, really small. That's just going to equal dA. All right, so, well, we want to find out, well, what is our relationship between all of these stresses at this point? And we'll just work through some really straightforward equilibrium. So the first thing we want to do is just sum the forces in the Z direction, and that equals 0. So just pointing up. So in the Z direction, we have this stress times the area of this block. So this stress times this area. So that's just going to be sigma Z times dA. So that's going up, and we have one down below, minus sigma Z times dA. Then we have a shear stress over here, plus tau xz times dA, and then minus tau xz times dA, and that all has to equal 0. Well, the areas are all the same, so we can factor that out, divide that out, that equals 0. Well, for this to be an equilibrium, we find that, well, all of these just kind of, this just gives us 0 equals 0. Well, that's not overly helpful. I mean, it's good to see that it's in static equilibrium, and that shows that, we do know that if we've got a stress on this side, it has to be on this side. Other things which it tells us is that stress at a point, if that stress is really, really small, you don't have any difference in stress across that point. And that makes sense, because this point is infinitesimally small. And so with that, all right, well, we know that our normal stresses and our shear stresses are going to be equal and opposite for equal and opposite faces. Well, let's look at in the x direction. Sum of the forces in the x equal 0. And we're going to have something very similar to up above, where sigma x times dA minus sigma x times dA plus tau of zx times dA times that little tiny area on the top to get that force, stress times an area, minus tau zx dA equal to 0. And again, we find out 0 equals 0. So not overly intuitive, not overly informative, but it does tell us that, at this point, we have to have equal and opposite forces. So, all right, well, we have, it's a 2D element, so we've got a third equation, and we can sum our moments, and perhaps that will tell us something a little bit more insightful than just 0 equals 0. So, let's sum our moments about C, so about this center point here. Now, when we do this, all of our normal stresses have 0 distance from C, so that moment equals 0. So the only thing that's going to contribute to the moment about this little block in this face are the shear stresses. And so let's write that out. So you'd have tau zx times dA times the distance a over 2 from the center. And then we've got another one coming, again, same direction, so we've got right-hand rule. So here, anti-clockwise is going to be positive, so plus tau zx dA times a over 2. And then we've got the x tau xz's going in the opposite direction. So you have minus tau xz dA a over 2 minus tau xz dA a over 2, and all of that equals 0. Well, let's do some simplifying here, and we end up with 2 tau z x minus 2 tau x z times dA times a over 2 equals 0. We can factor this out. The 2's cancel. And then we basically will work out that tau zx minus tau xz equals 0. So we can divide these out, divide out the 2. And what we're left with is that tau zx equals tau xz. And this is actually quite powerful and quite interesting. And what we'll find out is if we do this on each individual face, we'll find the same thing. We'll run through those just really briefly just to demonstrate. But what this is showing us is that if we have a shear stress, which is going up and down, well, we have to have an equal shear stress, which is going left and right, to keep this little block from spinning around, for it to be a static equilibrium. So it means that the transverse shear on a member always equals the longitudinal shear at a given point. And so we'll just round that out. Let's look at the other two faces, just to kind of prove that to ourselves. So we won't do the normal stresses where you can take my word on it that those are going to equal 0. But let's just draw them out here. So look at the orthogonal. So if we look at the orthogonal faces, and this will be Z and Y, X and Y, and again, all we're doing is just pulling them off of, Z and Y is looking this direction, X and Y is looking down this direction onto the positive. And we'll just draw the free body diagram. So stress in the Z direction, normal stress in the Y direction, and these are our shear stresses. So you have tau Z Y, tau Z Y, and tau Y Z, tau Y Z. And we'll call that C. And again, remember it's a cube, so the side lengths are all equal to A. So we sum moments at C. That equals 0. You get tau YZ times dA times A over 2 plus tau YZ dA A over 2 minus tau yz dA times A over 2 minus tau. Sorry, this should be zy. Zy is going opposite direction. Zy dA times A over 2 equals 0. You can see this has essentially the same form as on the other face, so we get tau yz equals tau zy. And finally, we'll just look at this last face over here just for completeness. Stress in the x, normal stress in the x, normal stress in the y, stress in the y, and you have the shear tau xy, tau xy, tau yx, tau yx, tau xy. Sum the moments at C equals 0, and you'll get tau xy times dA times A over 2 plus tau xy dA times A over 2 minus tau yx times dA, so just times that area, times the distance to the center, minus the shear stress tau yx times the area it acts over, times the area to the center for the moment. That all equals 0. And again, this will all simplify out to tau xy equals tau yx. So, as I said, this is a powerful powerful thing. This shows that anytime we've got a transverse force, well, there's an equal force acting longitudinally to it. And so, well, let's kind of, well, that's all well and good to see it on a little cube like this and go, okay, well, at a stress point, I know that there's my shear stresses now have to be equal. But what does that mean in terms of how we think about structures? Well, let's look at it. Look at in a macro sense. So if we have a beam that has, we'll just do a simply supported beam. And it's got two transverse loads on it. Well, we know now that, well, this is going to create a shear, right? So you're going to have a shear where, you've got your reaction force here and a reaction force here. So you have a shear force diagram that goes up, then down, down, then up. So it's like this. Well, that means that, well, we know we've got this shear force here. Well, we actually also have, in order to put this into equilibrium, well, we know we've got forces acting longitudinally, which are arriving from these shear forces. And they're going to act like that. Which means that as we load this up, for this to fail in shear, well, these are really trying to pull apart like this and pull apart like that. And so we end up with a simply supported beam. We end up with these diagonal shear cracks. And this is, you got diagonal. And this all falls out of this rationale that your shear stresses if you have a transverse shear stress, you have to have a longitudinal shear stress, and that's going to become important as we go on in these next few lectures, where what we want to look at is the distribution of these stresses as we go across a given member or over a given section. And that sort of little nugget of truth is going to help us derive those sections. And so one of the next things we're going to look at is, we've got these two stresses, but we also have bending stress, which are essentially normal stresses, right? It's uniaxial. For here you got compression on the top, tension on the bottom. Well, those have to add up with these shear stresses somehow. And that's what our next step's going to look at when we talk about principal axes and what direction is the material actually trying to pull itself apart. What is we've set everything up in these arbitrary coordinate states of up and down, left and right, but the stress state at a given point might not be aligned to those. And so that's what we're going to look at next. Hopefully this was a good introduction and sort of theoretical grounding for going from some arbitrary stress, and then we look at a very small three-dimensional cube on that, find out what our stress state is, find out that our shear stresses are going to be equal and opposite, and then that will eventually get us into problems which are a lot closer to what we are used to dealing with, or as a structural engineer, where we're looking at beams and how do these beams perform. And so with that, we're going to wrap up the lecture here.